Welcome back. And let me mention that the homework number 4 is due right now, and the midterm is 1 week away. So next Friday. Yeah, please feel free to turn on your cameras and let me, I guess, remind you what we did last time. Last time I explained the product formula for the exponential generating functions. So you have sequences f of 1, f1 of n, f2 of n, all the way up to f sub k of n. Right, so you have k sequences. And then you can define a new sequence, h of n, which is just the sum over, let me write it this way, t1, t2, the sum over all ordered k tuples of sets, which together their disjoint union is bracket n. Then you write f1 of t1, f2 of t2, etc. f sub k of tk. Then the exponential generating functions satisfy the product rule. H of x is f1 of x, f2 of x, etc. fk of x. All right, and I want to emphasize that here I'm asking, the sets could be empty and everything, but what's important is that they are ordered, because you have to know you apply f1 to the first one, f2 to the second one, so you can talk about when we studied Bell numbers, we talked about unordered set partitions like this, and they had to be also into non-empty blocks. But anyway, that's the product rule from Wednesday, and let me also summarize what we have computed so far. So at some point previously, I mentioned that I mentioned 5 sequences: 1, 2, 3, 4, 5, 6, 7, etc. That's the first sequence. It gives you, so each sequence gives you some generating function, and the Fibonacci sequence gives you 1 over 1 minus x squared, and the Catalan. So each next is sort of unexpected from the previous ones. 1 minus square root of 1 minus 4x over 2x, and you also have partitions, which was the infinite product, right? 1 over 1 minus x to the j. And finally, I also promised Bell numbers, but so far I haven't given any explanations. Yeah, so by the way, let me also mention that in your homework or midterms or whatever, whenever you compute some generating function and you want to check that you are correct, there is an easy way, which is to just use some software. So for example, even if you get an infinite product like this, let me try to demonstrate what I mean. So let's say I take partitions, right? You can compute the first few values, right? These are, you have 5 partitions of 4, and etc. So hopefully if you plug in this infinite product into, let's say, Wolfram Alpha, and then you ask for the Taylor series, you're supposed to see these numbers. But of course it's infinite, so you can't really do that. And the way, of course, the correct way is to just, if you care about the first, let's say, the first 7 terms, then you can discard all the terms which have degree higher than 7, right? All the powers of x higher than 7, you can just get rid of them. And so let's see, I made an experiment. Yeah. So So this is a screenshot from Wolfram Alpha. So you ask it to find the Taylor expansion of the product of the first 7 terms up to, and you want the expansion, you want the first 7 Taylor coefficients. And right on the nose, it gives you the same sequence: 1, 1, 2, 3, 5, 7, 11, 15. Yeah, I guess there's an extra one corresponding to n equals to 0. But anyways, the point is that if you want to check that after manipulating generating functions for a while, if you want to check that you got the correct answer, you can just ask it to Taylor to find the Taylor expansion of and computers are very good at that. So yeah, so the question for Bell numbers is what kind of functions should I plug in here to get Bell numbers as these coefficients? And yes, that's what I'm going to explain today, and some other stuff as well. Any questions so far? By the way, if you don't know the answer, then it's a good exercise to just try to imagine what, based on all this evidence, what's going to be for Bell numbers. It's probably not what you would imagine it is. Anyways, here's the next topic. The next topic is the exponential formula. And so far I discussed if you take some exponential or ordinary generated functions, you can add them, multiply them, and so far that's it. But you can do some other things with generated functions, right? You can also take composition. So let me first explain formally when you are allowed to take composition of 2 generated functions of 2 formal power series. So let's say you have 2 formal power series, f of x and g of x, formal power series. And so the necessary and sufficient condition is to assume that assume that f has 0 constant term. Then you can define the composition g of f of x, which just by definition is the, remember we talked about infinite sums, so it's an infinite sum of this form. So I'm assuming g of g of x is sum n greater than or equal to 0, g of n, x to the n, right? Just the usual formal power series. And then instead of x to the n, you plug in f of x to the n. And the claim is that this is a valid formal power series. So how do I prove? What's the proof of this claim? Right, yeah, that's correct. Thank you. So indeed, we had a criterion, right? We had, if you give me an infinite sum, I have a very easy way to tell whether it gives you a well-defined power series or not. And the notion is, what the claim is, that it stabilizes. Claim that this infinite sum g of n f of x to the n stabilizes. And what was the criterion? Well, it was that the minimum degree of the nth term, like the minimum degree of all these terms, has to go to infinity. And indeed, the minimal degree of f of x is equal to, well, it's at least greater than or equal to 1, because f has no constant term. So if you, so it's basically divisible by x. So if you raise it to the nth power, so the minimal degree of f of x to the n is greater than or equal to n. And that goes to infinity as n goes to infinity. And therefore, by some previous theorem, you get a well-defined formal power series. And you see this is very, you don't have to worry about like domain of definition or whatever. It's just all very formal procedure, but it matches the usual composition from calculus. And yeah, so now and that operation turns out to, like, so far it seems sort of unmotivated. Like, what is the combinatorial meaning if you take two nice sequences? Maybe one is Catalan and the other one is Fibonacci. What is the meaning of the composition from a combinatorial perspective? And well, so here is, let me first try to, before I discuss the general composition, let me first discuss the case where g is the exponential function. So first, important special case is g of x is the exponential of x. So that's where you get the exponential formula. Yeah, and that's where you see. So now I have to talk about partitions all of a sudden. So remember, we studied set partitions. Let me introduce the notation for that. So let capital Pi of bracket n be the set of all set partitions of bracket n. Right. So if you don't quite remember what are the details, so first of all, the number of blocks is unspecified, and so is the order of blocks. It doesn't matter. Right, and then also all blocks are non-empty. So the sequence is counted. The number of these set partitions of bracket n is the Bell number. Yeah. Does it make sense, or am I saying it right? Okay. So yeah, maybe should I try an example? No, let's pi of bracket 3, so I have to subdivide 1 to 3 into 1, 2, 3, 1, 2, 3. So I could either make the whole block, or I can make 1, 2 into a block and 3 into a block, or I can make 1, 3, 2, or 1, 2, 3, or there could be all singleton blocks. Right. So that's the kind of object I'm talking about. So okay, here's the exponential formula. the exponential formula. Let's say you have some sequence. Let f of n be a sequence which satisfies, which has starts with a 0. So f of 0 is 0. And then what I'm going to define is another h of n by, so another sequence h of n, which h of 0 is equal to 1, as you would expect from an exponential function, and then for n greater than or equal to 1, h of n is given by, so let's see, it's a sum over all elements of this capital pi of bracket n, s1, s2, all the way up to sk in pi of bracket n, and then you take f of the cardinality of s1 times f of the cardinality of s2, etc., f of the cardinality of sk. So in other words, if f is the number of ways to perform some task on an n element set, then h of n is, what you do is you split bracket n into non-empty blocks, some number of non-empty blocks, and then you perform this task on each individual block. So yeah, which later we're going to see more examples of this, like maybe the blocks are connected components of some graph, and then f counts the number of connected graphs or something like this. So yeah, the conclusion is that then the exponential generating functions satisfy that h, so the exponential generating function of h of n is the exponential of the exponential generating function of f of x. Is the statement clear, or? Okay. Let me try to prove it, because it seems kind of impressive. Right? You talk about some set partitions, and then you end up with this very simple relation for the generated functions, even though there is all these unnatural details, like the blocks have to be non-empty and unordered. Well, they have to be unordered because you apply the same task to each of them, right? If these f's were different, you wouldn't know to which block which task applies to which block, because the blocks are unordered. Anyways, I mean, it is what it is. It's a very natural formula, I think. So yeah, here's the proof. And the proof is very kind of short. It's basically a corollary of the product formula. So let's say so here, even though I'm using k, which is the number of blocks, it is unspecified. So I'm secretly summing over all possible values of k. But let's imagine that k is fixed. Suppose k was fixed, or maybe even greater than or equal to 0, or maybe it shouldn't be. Anyways, okay. Because so I'm defining it for n greater than or equal to 1, so I can allow k to be at least 1. Then instead of Bell numbers, you would get Stirling numbers of the second kind, right? But let's see what's going to happen. So you need to you need to the claim is that the exponential generating function corresponding to each fixed k would be given by f of x to the k divided by k factorial. So so let's see why this is true. First of all, if I so what is the reason? If I just ignore k factorial, right? So if I look at f of x to the k, f of x to the k is the exponential generating function, right? By the product formula, if you raise f of x to the power of k, is the exponential generating function of the sequence where you just take the sum t1, t2, all the way up to tk. Equal to bracket n, and then you just take f of the size of t1 times etc. times f of the size of tk, right? So and the two observations here are that the blocks could be empty, and also the blocks are, the order of blocks matters. So that's the sequence that you would get by just raising f of x to the power of k. Okay, and of course here there's the number of blocks is fixed, right? It's k, and the order matters. So that's why we divide by k factorial. I have the k factorial here, which exactly makes the order of blocks to not matter anymore. But what about the first problem? Right, because I want to count the sum where each block is non-empty. However, here I'm only counting, in the product formula, the blocks could be empty. So what is the, why does this work out okay? Oh, f of 0 is equal to 0. Yeah, thank you. That is correct. So we have this assumption on f, right? That f of 0, f has to have no constant term, and it looks like we want it because it's otherwise decomposition would not be defined. But also, if you actually, it's very sort of, we're very lucky here. Empty blocks give 0 contribution, since f of 0 is equal to 0. So all these ordered partitions which have an empty block are gonna give me 0 in the sum. So in particular, after you divide by k factorial, this becomes a sum over unordered set partitions into non-empty blocks with k parts. Does it make sense, or is it kind of too vague? Makes sense. Okay. All right, thanks. If it doesn't make sense, please stop me. I'm happy to explain more because this is a tricky proof. But it's sort of very short. So you just if you fix the number of blocks to be k, then the exponential generated function is given by this guy. But now you can if you sum over all k, and then you also have to include the case where so h of 0, we already have defined h of 0 to be equal to 1. So you get that the exponential generated function h of n x to the n over n factorial is equal to the sum of these terms, basically. Sum n greater than or equal to 0, f of n, f of x times x to the n over, well, sorry, no, f of x to the n over n factorial, which is by definition the exponential, the composition of the exponential function and f of x. This is by definition of composition of two formal power series. So yeah, that's the proof basically, and maybe it's hard to follow, but it's what's great about it is the applications, right? It's a very useful formula. Whenever you have some structure which is defined on all like these different components, then kind of separately on each individual component, like connected component of a graph, then you just apply the exponential formula to count one in terms of the other. Now let me give you an example of how to apply this exponential formula. And what is the example going to be? Can you guess what the first example is of an application of the exponential formula? Bell numbers. Okay, thank you. That is correct. Example, Bell numbers. Because indeed, Bell numbers count the number of partitions of bracket n. It's just the number of partitions of bracket n. So let's see, I'm gonna look at this formula, right? It's a sum over all. So, okay, what is h of n is the Bell numbers, and what is f of n? What am I supposed to plug in for f to get Bell numbers in this formula? F of n is equal to n. Let's see, f of n is equal to n. Then I would be multiplying. So that's actually an interesting sequence, right? I mean, I don't think it's quite correct, because you would get the sum over all partitions, and then each partition is going to have a weight which is the product of sizes of blocks. I mean, it's also interesting that, yeah, I wonder what's going to be the answer. But anyway, yeah, the actual answer should be f of n is equal to 1, because then you just count each set partition with weight 1. So h of n is going to be indeed right. It's just going to be sum over s1 sk in partitions of bracket n of f of number f of the size of s1, f of the size of s2, etc. f of the size of sk, which is, yeah, so each of these terms is going to be equal to 1, so we get Bell numbers. Okay, so what is the exponential generating function? F of n x to the n over n factorial, unless n equals 0, in which case it's 0. Okay, yeah, that is true. Let me try. If n is greater than or equal to 1, f of 0 is equal to 0. Yeah, let's be careful here. So, so indeed, the exponential generated function here is going to be e to the x minus 1. Right? You just get all the terms in the exponential in the exponential without the n equals to 0 term. So, therefore, by the exponential formula, the exponential generated function h of n x to the n over n factorial is equal to the exponential of e to the x minus 1. That turns out to be the answer for Bell numbers. So it's like e to the x minus 1. Which is, yeah, I don't know if that's what you were expecting for Bell numbers, but that's the. So let me try to convince you that this is indeed the answer. Let's see if I have another Wolfram alpha. So here is the exponential of x minus 1. So if I do the Taylor expansion, I get something that looks like this. While on the other hand, I think I have the table of Bell numbers somewhere. Yeah. So towards the end, it's much easier to spot. Like you get 877, 203, divided by the corresponding factorials, right? And then in the middle, it's sort of weird because, well, okay, let's see what happens in the middle. So 1, 1 is 1, 1 here, and there is a 2. So yeah, let me try. So x squared is actually 2x squared over 2 factorial, and then 5x cubed over 6 is actually, well, that one's all right. 6 is 3 factorial, and 5 is here. And then the next one is 5x to the 4th over 8, which is 15 x to the 4th over 24. So 15 is here, and yeah, anyways, it works out. The next one is 52 x to the 5th over 120, and etc. So yeah. And you can always, I mean, assuming your result gives a convergent function, you can always go to use some software to check yourself. Just compute the first few terms by hand, and then just check that because it's very easy to make a mistake of just, oh, cool, okay, thank you. Yeah, anyways, let me try to compute some other stuff. Because, as I said, the exponential formula is useful. So let me give you one more example of. Okay. Yeah. So the next example is. It's related to something we did in one of the early lectures, which was we were counting in how many ways can you sit a bunch of people around a circular table. So let me now. So here's the question. Find the number h of n of ways to split n people, so people are distinguishable, and people into, I guess, non-empty groups, right? Into non-empty groups, and have each group sit around a circular table. So remember, by sit around a circular table, I mean that I choose a permutation but two permutations are equivalent if they differ by a cyclic shift. Do you remember, or should I give a formal definition? Okay, some people remember. All right, so so the question is, what is h of n? Again, this is purely combinatorial problem. I'm not asking to find any generated functions, but as you see from the problem statement, you want to split split bracket n into some non-empty blocks, so it's got to be related to the exponential generated function. By the way, you can try to guess the answer. Can somebody guess what the answer is going to be? Okay, nobody wants to guess the answer. All right, so yeah, there is an each table for each group, right? So around its own circular table. Yeah. So you want to organize a wedding, and all these different groups of relatives sit in at different tables. So so here is the solution. What I'm gonna do is I'm gonna try to first find the exponential. I want to find the exponential generated function. H of n x to the n over n factorial. Okay, so to do that, I'm gonna need to apply the exponential formula. So what is the sequence f of n? Okay, e to the f of n is n minus 1 factorial. Okay, yeah, that is actually n minus 1 factorial. Is just the number of ways, let me write it this way. F of n minus 1 factorial, which is the number of permutations modulo cyclic shift. Right? That's the number of arrangements of people around a circular table. Okay, so the exponential generated function of f of n, f of x is the sum, n greater than or equal to 0, f of n, x to the n over n factorial. So f of n is n minus 1 factorial. Wait, by the way, so this is if n is greater than or equal to 1, and f of 0 should be 0. And that's, if you have 0 people, then let's pretend they cannot sit around the circular table. I mean, it doesn't really matter. But to apply the exponential formula, I need to set f of 0 to be 0, which is sort of consistent with it's like minus 1 factorial. Anyways, so I have this exponential generated function, which is just the sum for n greater than or equal to 1, x to the n over n. Right? So it's like x plus x squared over 2 plus x cubed over 3 plus etc. So can anybody recognize the corresponding Taylor series? It's the natural logarithm of something. It's e to the x. Well, for e to the x, I would have to have factorials here. But yeah, actually, it is true. So this is the Taylor series, almost the Taylor series for the logarithm of 1 plus x. Yeah, I think Okay, let me try to remember. The logarithm of 1 plus x is, I think it should, right, it should be logarithm of 1 minus x. But then for 1 minus x, I think it's like negative, well, okay, so hold on, let's try to remember. If you take 1 plus x, is going to be x minus x squared over 2 plus x cubed over 3. Or is it? No, it's going to be different. Wait, hold on. No, it's fine. Minus x to the fourth over 4 plus etc. So if you take, anyways, my point is that I think you need to take negative logarithm of 1 minus x. Because if you, without the minus sign, you would get minus x squared, minus x cubed, etc. Right, so you have to just take the derivative. Okay, right, if you take the derivative of this guy, then you're gonna get something something like 1 over well, you have to have, oh, it's just literally this. Okay, yeah, okay. Yeah, then if you, all right, yeah, then anyways, the point is that x plus x squared over 2, yeah, you could take the derivative and then etc. So the claim is that capital F of x is negative, well, natural logarithm of 1 minus x. And now I'm about to apply the exponential formula. H of x is the exponential of f of x, which is the exponential of negative natural logarithm of 1 minus x, which is what? It's just, oh yeah, I should have given you an example. Okay, anyways, it's just 1 over 1 minus x. So now I'm gonna use it, right? I got a very simple result. So now I can use it to find h of n, which is, I was supposed to extract the coefficients of, these are the coefficients of x to the n over n factorial. Okay, I can, 1 over 1 minus x is the sum of just x to the n, which is the sum x to the n over n factorial times n factorial. So the answer is that h of n is equal to n factorial. So, which sounds weird. It's, let me try. Maybe I should have tried to give you an example. I think, yeah, I should have computed examples beforehand. But anyway, so let's say maybe h of 3. I want to have 3 people sit around some number of circular tables. So let's see, I can have a single circular table where they all sit together. That's one option. Or I can split 1, 2, and 3, and that counts once, right? Because there's another option, which is I could have 1, 3, 2. So these two circular tables are different. Modulo cyclic shift, these are not the same permutations. Or I can do 1, 2, and 3, or I can do 1, 3, and 2, or I can do 1 and 2, 3. So if you have a circular table of just 2 people, it doesn't matter in which order they come. And finally, I can have 1, 2, and 3 all separate. So h of 3 is equal to 6, which is 3 factorial. So as usual, I'm going to ask, can you find a bijective proof? Which, yeah, I haven't thought about it, but this is probably hard. I'm not sure. But I mean, yeah. So that's another application of generating functions to just straight plain combinatorics. You could just get n factorial from some weird manipulations with exponentials and logarithms. Anyways, yeah, so that was the exponential formula. In the pre-recorded lecture, I'm going to explain what happens in general when you take decomposition, but that's it. So yeah, I'm out of time. I think, oh, I have 5 more minutes. Yeah, well, anyways, I think now is a good time to stop, right? Unless, yeah, now is a good time to stop. So if you have any questions, let me know. If not, there is no homework. I'm going to send you some practice problems for the midterm today, and that's it. Have a good weekend, and I'll see you all on Wednesday. Thanks.